trying to use that model for exactly the same task, you might use it out of the box. But frequently what people will do is they'll take this model and they'll make some small modifications. More recently, it could even be self-supervised training. So let's think a little bit about how those initial models are trained. These are going to be reused over and over again by a large portion of the community, both in the academic community and also more broadly. So it's really important that when we think about these canonical models, when we think about the fact that they're going to be used in so many diverse scenarios, we need to have some understanding into when they're going to work. How reliable can they be? Can we communicate this to people so that they can better understand? So of course, we all know that the first phase in a particular data set in mind. So I just mentioned one example where people were using the ImageNet data set. You could use any other data, but this is, as we know, a central part of defining the model. What data are you using? If you want it to be a supervised learning problem, you're going to have to define some label space and get some labels. So if you want to recognize dogs, maybe you'll have to be able to.
Sorry to interrupt, but we cannot see slides, I think.
You can't see slides.
Yep, multiple people. What? We cannot see presentation.
Okay, 1 second, we will fix that. Can you see them now?
Yeah, we can see it now. Thanks.
Okay, great. Just, another joy of the hybrid conference experience. But hopefully we have everybody on board now. Okay, so you have these annotations, and now you can go ahead and train this model that you're going to pass along to people. And this has been such a pervasive part of the learning process that, of course, one of the key phases that happens is that we want to collect some large databases that people can reuse over and over again. So for canonical tasks like classification, of course, there's the famous data sets of ImageNet and Places. For detection, you might have generic detection of object categories like COCO, or you might have application-focused data sets, the city-space data set for self-driving. These data sets are kind of collected frequently as a benchmark to be able to start to establish how well a model that might be passed around to other people is going to work. But we have to think a little bit deeper about how these models that are designed, developed, and trained on these data sets are then evaluated. So frequently, the way that a benchmark is going to establish its validation, which is then going to be kind of passed around along with a model in order to specify how well we think a model works, what you'll do is you're going to have a held out portion of this same data set, and you're going to use that in order to measure some aggregate performance metric, like perhaps you're going to measure accuracy when we're talking about ImageNet. So this says that for these particular object categories, you can have an expectation of this particular performance. So for a model that's this large ResNet model from 2017, it was looking like performance was very high. So we now remind ourselves of this transfer learning scenario. Somebody's going to take this model, they're going to think to themselves that I have a performance that's close to 100% on this seemingly complex task of recognizing 1,000 object categories. And you would ideally hope that that is a reliable measure that could be used in your scenario, that you could say that if this model works so well here, it should work for me too. But we know that this isn't really the case. We know that there are limitations to how you can reuse these models in practice. It's of course better to reuse some information, but we have to have some better understanding. We know that these systems are going to be used broadly by lots and lots of people, some of which are maybe experts like those in this room. So if we take this model that was trained on ImageNet, one way in which it can fail is if some of the assumptions about the data change. So ImageNet is a static data set. If you want to apply the model that was trained on ImageNet to recognize things like dogs to the frames of this video, you can't recognize the dog. And really that just has to do with the distribution shift or dataset bias between the ImageNet dataset version of dogs and the way that dogs appear in this video. In the ImageNet dataset, we have scraped images of dogs that people have decided to share as still frames. So the types of photos that people want to share of dogs as still frames are going to have a bias towards having the face of the dog visible, a bias towards having the dog in the center of the frame, and have, in general, higher resolution than you might have seen in frames of a video. Now, if we're talking about videos, people don't necessarily take 20 videos and then upload the action, like the dog running. And so instead, the frames of this video, perhaps because of the high frame rate, are going to be lower resolution. You're going to have blur from the subject and the frame, and you're going to have a wider variety of poses than you had in the original still image data set. So all of these changes, though subtle, do lead to degradation in performance of a pre-trained system. If we move on to more complicated tasks beyond classification and think about the task of semantic segmentation in driving scenes, first of all, these data sets tend to be smaller than the still image data sets because it's quite expensive to collect and annotate the frames for these types of applications. And the representation that's needed in order to capture the diversity of the world is much larger. You need to be able to think about all kinds of different cities, all kinds of different weather conditions, and all types of different sensor capture processes. If we try to ask what would happen if you don't have all access to all diversity before you get started and train this initial model, what would be the result? We can imagine thinking about one particular scenario where you're trained primarily on sunny weather conditions and have an underrepresentation of other weather conditions like snow. So your sunny weather, you have a model, it seems to be working really well. You do your benchmark task to evaluate performance and aggregate across, again, a distribution that's primarily sunny, and it seems to work well. But if we look at a single image from the snowy time, what we find is that this model fails to recognize a lot of the surfaces that have snow on them, like the road and the sidewalks. It's actually confusing them here with buildings. Now, this is a big challenge because recognizing roads and sidewalks are actually something that we think we're very good at. If you were to take that initial model that was trained and evaluate it, it had very high pixel accuracy at recognizing roads. So the fact that it can degrade egregiously in this case is an issue that needs to be clarified and illuminated. There are other circumstances under which models can fail. Like, for example, if minor corruptions that hadn't been seen at training time appear. There's a data set that was introduced in 2019 that showed that even for the same exact data that was being evaluated before and after corrections, you could see up to a 20% drop in accuracy. And then, of course, at the extreme example, if you have a malicious actor in the loop, they have the ability to make minor perturbations to images that have dramatic impact on the results of your predictive performance. So classically, the adversarial examples, the hallmark of them is that small, seemingly noise-like images, very low magnitude, in such a way that once you've added them to the original image, they aren't going to change the perception of the image to a person, but they change, those noise images are selected exactly to be able to modify the predictive output of a model. There's been lots of study into this work, including at this conference. There was a workshop just yesterday that were looking at this problem as adversarial robustness and robustness more generally. So there's all of these different ways in which models can fail as a result of the data input or visual appearance changing. And it can change for many different reasons. It can change for benign reasons, like a curation or a capture bias, as it did with the still images to the video. Or it can change for subtle reasons, like corruption happened to images, or even an adversarial reason. A lot of these works that I showed so far focus on tasks like classification or more broadly just visual recognition, but visual recognition tools are also used as part of a larger pipeline. So one work that I want to highlight briefly is a benchmark to understand how corruptions to the input of your visual space, when included as part of an embodied agent pipeline, can reduce the performance. This is something that isn't necessarily, we study these things in isolation, but again, if people are going to be taking weights from an initial model and adding it into a larger pipeline, we need to understand how they might degrade. So just very briefly, for those who aren't familiar, in the embodied navigation task, there's usually two different goal tasks that people study, point nav and object nav, navigating either to a point of interest or an object of interest, like go to a sofa. The agent will have input to just sensory information like RGB or RGB in-depth images shown here. And this top-down view is just shown for visualization. The agent doesn't have access to a map. It's just reactionary depending upon its visual inputs. So the agent will be given a goal task like traveling to a particular point. And it will then, once it travels to the particular point, it will be rewarded if it reaches it in a timely manner. So one of the issues with these benchmarks that existed today was that even though it appeared that you're having very, very high performance, so these agents were getting close to 100% success rate on some of these tasks. If we analyze how they're being used from training to test, what is actually being modified, it was mostly focused on scene layout variation. And let's focus on what would happen if something changed in our sensor, meaning our visuals changed, or something happened to change anything with the dynamics of the scenario. So in this RobustNav benchmark, what's being introduced is an ability to understand, evaluate, measure how the performance might degrade in response to changes in the visuals. Some examples of the corruptions for the visual space include things like what were to happen if there was motion blur, or lower lighting conditions, or if there were debris that ended in the camera. For dynamics corruptions, there were really just two different types. One that emulated things that would result from an environmental shift, like a change in friction of the floor, or things that would be a result of the agent itself having a malfunction. So once we do that, oh, for some reason the videos aren't playing. Just imagine that there's a video. I'll describe what it would show. So in general, what would happen is the agent would be able to perfectly navigate both successfully but also quickly to the target of interest. And just checking. And once you change some of the input visuals, even something as simple as changing the lighting conditions can make the agent have difficulty to navigate to the point of interest. And for some corrections, it could fail entirely. So the reason why I bring this up, the difficulty here, is that this is yet another scenario where we have a benchmark that is trying to establish some measure of generalization. But as we start to get higher in performance and gain some confidence in the performance of the system, it's going to be more and more adopted and reused out of the box. But we need to be careful to make sure that we actually accurately represent the expected performance in all deployment scenarios, which may involve changes to your sensor. You may get a crack on the camera, or spatter may appear, or the friction of the floor may change. And so as we continue to think about, we know the ways that models can fail, we need to make sure that we properly are evaluating them before they're going to be reused widely. Now, of course, this is a simulated environment, and frequently in computer vision, we do use simulated data. And the reason why we use simulated data is it's going to be much cheaper to be able to use in practice, and it might allow us to actually generate all of these scenarios that are potentially going to be experienced at deployment time, both for evaluation, as was done in RobustNav, but also for training. But there is a gap between simulated data and real data. So one thing that we have to take into account is any performance that we evaluate on our system in simulation to be used out of the box on real data. One popular example that's used within the domain adaptation community is to think about training on synthetic driving data, like from the Grand Theft Auto game, and then adapting it for use in real data, like on the Cityscapes data set. More broadly, domain adaptation is the problem statement where you have access to a large labeled source data set. It could be from your curated data set like ImageNet, or it could be images that you have access to in a product, or it could be your same data. In any of these cases, the idea is that you have to be adapted or specialized when the visual appearance changes. And this appearance change can occur, again, because of something like capture or curation bias, or it can be because you would like to be able to recognize these objects as they appear in the wild, or because you want to be able to take your simulated model and use it in the real world. So if we're thinking about the fact that these models degrade, these models aren't working as well out of the box, maybe there's something we can do about it. Maybe we can actually start to adapt these models in response to observing changes in the visual world. A really popular class of techniques in this space is called domain adversarial adaptation. And the way that this works is that you imagine you have access to a large labeled source data set. This is going to be that model that you reuse over and over again. And your performance is quite high in domain for this source data. The challenge is that your performance degrades on this different visual appearance, this target data. And so we'd like to mitigate this problem by performing an alignment in feature space. The way that we measure whether or not the two distributions are aligned is we can train a domain classifier whose job it is to distinguish between features from the source and target domain. If you can distinguish the two, then the distributions are far apart. So we'd like to resolve this. We want the distributions to be aligned, because if they're aligned in this feature space being used for the supervised tasks of classification in this case, then we have a better chance of being able to use it out of the box on our target data. So to update this in order to align the two, we're going to use an adversarial loss, which tries to confuse this domain classifier, thereby rendering the two domains indistinguishable. There are many Zoom notifications coming up. All right, so once we do this, we have a simulated image. And the simulated image, in this case, is from the Grand Theft Auto data set. And what we're going to do is we can perform image-to-image alignment using something like a cycloban in order to produce an image. You can use full domain space in order to produce a model that allows you to better evaluate or better adapt your simulated model for use in the real world. So this is an example where you have a cityscapes image in the upper left-hand corner with the ground truth in the upper right-hand corner. Before adaptation, meaning just looking at your model out of the box trained in simulation, it doesn't work very well. After using this type of domain adversarial alignment, you're able to start to see improvements. And in particular, what I want to highlight here is that a lot of the improvement actually comes in the form of the classes like road. You do have some extra improvements here, like this pedestrian or the street sign in the background, but the majority of the improvements, and then we see this over and over again, actually comes in the form of the head classes, or the classes that are most prevalent in the data set. So for an application like self-driving cars, the most prevalent pixels for semantic segmentation are the ones that are going to be corresponding to road or building. And so that's where we see most of the improvement. And actually, you see relatively less improvement on the rare classes. And this is an artifact of this type of alignment technique. But when we're talking about real world applications, we're talking about people trying to use these systems for adaptation out of the box. The difficulty here is that your data set hasn't necessarily been curated. So this limitation of using marginal statistical alignment techniques is a real one that we have to contend with. It means that our rare classes are not going to be as well adapted. It means that overall, we're going to be biasing our adaptation towards the common classes. So coming up next, I'm going to have Viraj step up here, and he's going to tell you a little bit about what we can do to help mitigate these performance losses when you have the situation of a long-tailed distribution. We'd like to move beyond this idea of marginal statistical alignment techniques, and instead start thinking about how we can do alignment that more and the rare classes.
Okay, so thanks, Judy, and I'm Viraj. Excited to be here, and I'm going to be continuing talking about the problem of adapting models to label imbalanced data so that you don't end up with poor performance on rare categories that may still be really important from your application's point of view, and so that you have more reliable computer vision systems. So in the real world, as you mentioned, you may be able to curate your source data sets to say have a balanced label distribution, but we really don't have any control over the target data set. And in fact, many real image data sets, as shown on the right, tend to have a long talked about actually have been shown to, because they Sorry about the technical difficulties. So as I was saying, so we have where the boundaries are shown in gray, and some instances like this triangle that you see on the left and the circle on the right are actually misaligned, right? And if you try and do self-training here and say perform entropy minimization, you're going to actually increase the model's confidence in its own predictions, even if they are incorrect, and push them away from the decision boundary, effectively reinforcing model errors and leading to this kind of domain misalignment. So the main challenge here is that the model is being adapted in response to all observations, but the goal is to try and adapt only on reliable observations that have a high probability of being correctly classified. And we explore this idea in, sorry.
Yeah, now right now it's Wi-Fi. I don't know. Yeah, no. Yeah, let me try to. You can.
Should I switch off my video?
Yeah.
Should I keep my video on?
No, you just take it off.
Take it off.
Yeah, I think it's already on.
Oh. All right, sorry about the delay. So I'm just keeping, for people on the call, I'm just switching off my video right now because the internet connection is quite unstable. Hopefully that'll help. So as I mentioned, we're trying to identify reliable target instances on which to self-train. And one way to do that could be, say, model confidence, but that's been shown to kind of be unreliable under a distribution shift. And so we instead use this notion of predictive consistency across image augmentations, which I'll make more concrete in a couple of slides. And so we can then go on to identify some target instances here, shown with this green tick, as reliable and others as unreliable, and then only selectively increase model confidence on consistent instances or reliable instances and reduce it on unreliable ones, hopefully leading to more robust domain alignment. So here's how the algorithm operates. So first, you start off by sampling this a labeled source image, in this case a sketch of a bear, and optimize a supervised loss. And then you sample an unlabeled target image and get a prediction from the model. In this case, it also predicts that it's a bear. We then apply a committee of label preserving data augmentations to generate these images that you see here and get predictions from the model. And you'll notice that the model prediction in this case actually changes to dog. And we can pass all of these to this selective entropy loss, which operates as follows. So it's simply going to measure the predictive consistency across all of these images and use a simple majority voting scheme. And for instances for which the predictions are mostly consistent, it's going to mark those as reliable and minimize the model's predictive entropy to increase confidence. And for unreliable instances, we can maximize entropy to reduce confidence. So that's the entire approach. And you may notice that it's like relatively simple compared to, say, some prior work on domain adaptation via adversarial learning. But the main notion and insight here from a domain adaptation point of view is to introduce this notion of instance reliability and only do selective adaptation. And that can lead to much better performance, especially on underrepresented categories, which are particularly important from a reliability point of view. And so as results, we look at the standard classification benchmarks, such as this 40-class subset of the popular DomainNet dataset, which is natural data distribution and label distribution shift that you see on the left. And here are some of our results on 12 shifts from this benchmark. And we're interested in transfer performance to the target test set. And we're looking at 4-class average accuracy. So first, we know that a model without any adaptation, that is just trained on the labeled source data, gets 66.8% accuracy. And we benchmarked some baselines based on distribution matching and meant to overcome just label shift, and find that they do not offer very strong improvements. And then we look at some recent methods that are meant to counter both data and label distribution shift based on relaxed distribution matching, confidence-based self-training, and entropy minimization with other losses. And we find that the self-training methods in particular are a little more robust. And finally, our method, we find, does much better in this particular setting, and also sets a new state of the art on most of the shifts that we study. And in follow-up work, we try to extend this to a more realistic and complicated task of semantic segmentation. So seen here on the top left is an image from the Cityscapes dataset, and we are trying to do adaptation from the Grand Theft Auto game to this Cityscapes driving dataset. And here is the ground truth annotation for this image. So before any adaptation, taking a model that's just trained on the source data set, this is what the predictions look like. And if you go on to apply unconstrained adaptation on all of the model's predictions, so you self-train on all of them, this is what you get. And you'll notice that the model's performance is measured by mean intersection over union does go up. But most of these gains are on well-represented categories like road, shown here in purple. And if you actually zoom in on tiny objects such as the street sign here, performance actually degrades when you do unconstrained adaptation. But if you do selective adaptation using a similar algorithm as I was describing earlier, you can actually recover performance again on these small objects categories and also boost overall performance substantially. And in very recent work, we tried to kind of validate the same pipeline in a more modern setting where we try to adapt vision transformer models initialized with self-supervised representations, which is rapidly becoming the de facto pre-training strategy for deep models. And we, in particular, methods like the masked autoencoder approach that was recently introduced, which learns to reconstruct an image given a highly masked version of the same image. And as before, our idea is to use predictive consistency. But we find that in this case, a superior alternative to using random augmentations is to instead match the self-supervised proxy task. So in our case, this corresponds to consistency under masking. And so we can actually do attention condition masking by leveraging the VIT attention mechanism to generate these sorts of masked images that you see on the right. And then you can probe the reliability of this target instance by measuring predictive across all of these images. So far, we've been talking about performance degradation from bias in the form of curation and weather and sensors, but a less studied bias is one with changing demographics when systems underperform on underrepresented subpopulations. So prior work by Dries et al. Has shown that many modern computer vision datasets significantly overrepresent the developed world. And for example, for ImageNet, most of these images were collected primarily from North America and Western Europe. And that clearly is in stark contrast to the distribution of world population shown here in the bottom right. And this is a problem because models trained on these data sets then go on to massively underperform on images from underrepresented geographies. So because these models have primarily seen soap look like this image that you see here on the right, this model, when evaluated on a bar of soap from Nepal, the model will mispredict it as things like food and cheese and bread. So far, since we've been talking about domain adaptation as a way to match representations between the train and test sets, we tried to ask whether domain adaptation can fit this setting and help make object recognition models work for everyone. And this was presented at a workshop earlier today. So the goal is to take models that are trained to recognize, say, statues from North America, shown here on the left, to also recognize statues from Thailand and South Africa and Vietnam, which currently the model is not doing very well. And to do this, we collected two geographically diverse benchmarks based on the Dollar Street and GeoIFCC data sets. So, and here source and target represent geographically distinct locations. So, and you notice that even for a simple category like toothbrush, visual appearances can change quite significantly across geographies. So how do existing unsupervised DA methods fare? So first, we set up two adaptation settings, for instance, from North America and Europe to the rest of the world, and measure the performance of a model trained and tested on the target set, and a model trained on the source set and tested on the target set. Performance gap between the two is what we're trying to close. And we applied some off-the-shelf unsupervised DA methods, but unfortunately found that they offer limited to no improvement. And so off-the-shelf methods just don't seem to work in this setting. And when we probe this further, we find that this is because of the existence of additional challenges beyond data distribution and label distribution shift. So the first is this notion of context shift, where object surroundings can change a lot across domains. So you'll see toothbrushes primarily in bathroom environments in North America, and there's a lot more diversity in surroundings for the same category in your target. And the second is a notion of subpopulation shift, which is a shift in intra-class distributions for a given category. So, for example, for a category like cleaning equipment, it primarily means images of vacuum cleaners in North America, but it primarily corresponds to images of brooms and mops in other parts of the world. And this shift in intra-class distribution also poses a challenge to adaptation algorithms. So to conclude, I think we need to call on people to develop more specialized solutions for this geographical DA setting. So that's all from me, and thanks for listening. I'll hand it back over to Judy.
Thanks, Raj. So I just want to conclude very briefly. We talked about a lot of different things today. This is a tutorial. We're talking about human-centered computer vision. This particular talk is focused on thinking about ways in which we can make sure that our vision systems are more reliable for use for lots of different scenarios and lots of different people. People are going to take our models and use them out of the box. And we'd like to make sure that we can have some measure of a reliability goal. We want to make sure that they're going to work as expected at deployment time. But this can mean many different things. This can mean that you want to make sure that it works as your appearance changes in subtle ways, like because of the weather changing. You'd like to make sure that it works even as malicious actor intervenes. And you'd like to make sure that it works for all people around the world. So these are the different scenarios, and each one of these scenarios might necessitate different mitigation efforts. The first thing that we would like to say in conclusion is just that we need a wider diversity of benchmarks to be able to capture and measure all of these different sources of variation and different ways in which our models will be used. And then we need new algorithms that allow us to introduce a sense of resiliency to our models. We want them to work out of the box as much as possible, but we also want to be able to specialize them or adapt them. And especially we want to be able to do this in a reliable way that can be done without needing to have an expert in the loop. So the two works that we highlighted here today, if you're interested to look them up, was a benchmark for robustness in embodied navigation, as well as an algorithm for adaptation, especially for adaptation in long-tailed or labeled distribution shifts. I want to thank Raj especially for being a co-presenter, as well as the other members of my lab who have contributed to some of the work that I highlighted here. And I think that we have a few minutes for questions at this time. Any of you have any questions? There's a very bright spotlight right here, so if anybody stands there, you might have to like wave. Okay.
Thanks for the talk. I was wondering if you have data on how commonly directly reused Adversar versus training from scratch. Like how many people learn directly using Adversar?
So what I would say is this. It's very, very common within our community as we design new algorithms to download weights of models. If you're in a company, you might not download weights. You might be training from scratch on data that you collect, but you're going to be having a similar problem that exists here, meaning that you're going to have an initial data set that's large, and you're going to be reusing those weights for new circumstances. And if you're not a giant company that has a large annotation budget, you're going to have to be doing some sort of reuse of other data.
Thank you so much for supporting. We struggle a lot with measure relevance given times. We'll have to keep this to say, hey, this model in the wild is biased in the versus again, it's categories that it's even more complex if it's a repeat of we have like getting data point to distribution or depiction where we can probably repeatedly systematically measure the bias in the real world scenario. The first question is, in the wild, how can we measure the bias beside luxury of categorization type of problem? The second question is, what about CGI data where computers use in the retail world, we need every wide technology. What are your recommendations to take into account the fact that we have these images during the training, keeping into account that the data is highly imbalanced, only in scale data? How can we generalize or take more of taking into account? These images are what in the wild you will see very, very complex. Congratulations on bringing your idea.
Yeah, so thank you for the question. There was a lot of interesting points in there. I'm gonna, it was a long question, so I'm gonna reiterate 2 points. One of them, which is how do we measure bias? That's a great question and a hard question in general to answer. And we didn't have time to talk about it in today's tutorial, but in general, my personal belief is that we need to have some better ways to illuminate bias in an unsupervised way. So we need to be able to automatically identify parts of data, or even when we receive new data, have a sense of reliability there. And if we don't have that, then we're kind of stuck in the scenario where we have to pre-annotate all sources of variation and then use our standard tools of validation with benchmark systems, which we know is sort of fraught. We do need benchmarks. We do need that to have kind of a more robust measure of how well we think it will work across different scenarios. But at the same time, if we want to truly understand bias and predict what's going to happen in any individual scenario, we need to have something that will work more on instances. And the other question, let's see if I can remember it. Do you remember the other part of the question? Does anyone remember? Oh, yes, right. So the other thing is, and I encourage you to look up the topics of domain generalization, which we didn't talk about today. But in brief, the way that works is that you're pre-assuming that your data kind of is, you want it to have enough diversity or a large enough set of options that can perhaps match what you will see in any test time. So for example, with your white background, you know that this doesn't mimic what you're going to see at test time. And so some of the things, like the simplest things that you can imagine doing, is doing some sort of augmentations. And there's a rich literature, especially in the robotics community, on doing different domain random augmentations to be able to use low fidelity simulated data or data that has a white background, and then reuse it in scenarios that have more complex backgrounds. And surprisingly, so far, it seems like you don't even need to have hyper-realistic augmentations in order to get the value of these approaches. What's most important is just that you kind of break the idiosyncrasies of the initial data set. So making sure that there isn't a large swath of only white. Even adding some kind of like random color blocking and noise helps break the learning of some of those features. Okay. Oh, one more question.
This is just a sort of general question. So I don't see computer vision class that we tried to do. The example you had with bar soap from Nepal. But how likely is it that I'm going to see that in isolation from its environment? So the more realistic situation seems to be that if I'm in Nepal and then I can see it. And I will guess when I'm in the bathroom, given that there's nothing else, there is soap like that, it's still soap, right? So I'm just curious as to how you would factor that in. I mean, We have set up a lot of computer vision tasks as essentially sort of superhuman tasks that don't have to do with what humans actually
Yeah, so that makes sense. I guess, and that example in particular, I think might be quite, it's kind of cherry picked and it's particularly challenging. So what we were trying to do in that specific setting was to see if the model has only seen, soap images from, say, North America, and it has seen very few examples of bars of soap. Then is it able to also generalize to bars of soap from other parts of the world? Context and the surroundings have changed quite a bit without access to labels, but you do have access to the data, right? We're trying to align the features for these two domains without access to labels. And I guess the intuition is that, then you can perhaps deploy your model in novel geographies without having to collect a large data set for each setting. And at least from our preliminary findings, it feels like doing it in purely unsupervised fashion is really challenging. And that's kind of, to your point, maybe we do need to collect some labels in the target as well, if not for the entire data set, at least for a subset. And maybe that's sort of a more tractable task to solve.
I was just thinking that if we had some sort of taxonomy or
Right.
it might make the problem less artificial. I'm being very critical here.
Right.
I'm not saying that it's perfectly fine.
Right. Yeah, that makes sense. Yeah, I think in general, having more information in the form of a taxonomy in your label space or having more annotations per image, having any labels at all to begin with, or metadata in the form of where this came from so that you can learn like different representations. All of those are perhaps sort of ways towards making this task more tractable and also not like expecting too much from our models. Thanks for the question.
Okay, so let's thank our speaker, Raj, and Professor Hoffman.
We're running all of this through one. You don't have another USB-C. That could be the problem. We're asking too much out of that one dongle. But you've got, as long as you've got plenty of power, but now it's I've got green light now. We didn't have that